If we have an index on the join columns of one of our tables, the optimizer has the option of choosing another algorithm called index nested loops join. And let's look at it here. Basically, the idea with index nested loops join is we take the inner loop of nested loops join and we replace it with an index lookup. It kind of looks like this. For each tuple little r in R, do. For each tuple s in S that matches, do. Return the result of the pair. Now, the magic, of course, is in that inner loop where we only look at tuples in S that match. How do we do that? We do that via a lookup in an index. So for every tuple r, we take its join value r sub I, and we do a lookup in the index on S sub j to find the matches. There may be many matches per tuple of r, so it is a nested loop still. Now the cost of evaluating index nested loops join is a bit trickier than what we saw with our previous join algorithms. So let's have a look here. Roughly speaking, the cost is to scan r, and then for each tuple of r, it's the cost of finding the matching S tuples. But we have to deal with our various index variants, the alternatives, and whether it's clustered or not. So if the index uses alternative 1, the cost per tuple of r is the cost to traverse from the root to the leaf of the tree on S, which is usually 2 to 4 IOs, and a query optimizer will usually know the height of an index as a piece of metadata, so it can actually calculate that directly. For alternatives 2 and 3, we have to get the cost of looking up the leaf node, which again is 2 to 4 IOs for a B+ tree, and then the cost to retrieve the record from the heap file via record ID. And this, as we know, is different for clustered and unclustered indexes. So for a clustered index, we do 1 IO per page of matching S tuples, and for an unclustered index, we simply do 1 IO per matching S tuple. And so the tricky bit here is that we don't know how many pages of matching S tuples there are for each value of R. So let's work through this with an example. Here's our schema, okay? It's the same cardinalities for the tables, same schemas. The only change is an index on SID. So the unclustered cost is going to be the cost to scan R, and then for each tuple of R to both walk down the index and access the tuple. So that's bracket R, the number of pages of R to scan it. And then for each tuple of R, vertical bars R, it's the cost of search plus heap access. The clustered cost, on the other hand, is bracket R to scan R, and then for each tuple of R, we just do the search. And then we're going to say that for every distinct value in R's join column, we're going to do a heap access, but we'll only do one heap access per distinct value on the theory that all the matches are probably on the same page or on a nearby page where the IO is sequential and much faster than random IO, so we just won't count it. Okay, so going through some specific numbers here, if we have a B+ tree of height 2, remember that's 3 IOs from the root to the leaf, the way we're numbering things in this class, then the cost here is going to be bracket R, 1,000, plus vertical bars R, 100,000, times 4 for an unclustered cost, 3 to search the index, and 1 to do the heap access. 401,000 IOs total. For a clustered B+ tree, it's 1,000 for the bracket R, plus 100,000 times 3 to search for every tuple of R in the index on S. And then it's the number of distinct values of R times 1. So that's 301,000 plus some x, which is the number of distinct values in R. We know that the biggest x could be is the number of tuples in R. It's 100,000. So x is at most 100,000, probably less. And so that's where the potential savings is for a clustered B+ tree in this index nested loops join.